included one of the terms out of the two. So let's look at the other one. Okay, now the other term is here. It's the nonlinearity. Now, it's not that often you can solve nonlinear ODEs exactly. Sometimes you can. Okay, but this one here, you can solve it exactly. In fact, the solution to this is just simply here. Let me write it down for you. There's its solution. Pretty nice. Give it the initial value, multiply by this phase factor, done. So what you see here is the two pieces, each individually, I can actually solve exactly. I don't have to put this in OD45 either, right? What is the big cost for us? Part of the big cost for us is when we take time steps is we have to develop these time stepping algorithms, right? We have to say, okay, OD45 to marching forward into the future. I already have the exact solution in the future. So if you think about it, you could say, well, this is a perfect place for using the split step method. Because in the split step method, what I could do is take a delta t of this and a delta t of that, and I have exact solutions for both. So I'm not even doing time stepping anymore. I'm just taking my initial condition, take a delta t of each one, and I know the exact expressions for them, and I got myself into the future. So let's look at how this might look. All right. So here's an algorithm for doing this. All right, did I spell that right? Okay, good. I think I did. All right. Sometimes when you look at words, they just... See, that's why I told you not to spell in public. All right. Here's the algorithm. Start off with your initial condition. U naught. So this is your initial function at, let's say, time 0. Okay. Now, we could do one of two things. We could either take a step in the dispersion first or in the nonlinearity second or vice versa. But let's go ahead and just take a step first in the dispersion. Okay? Step 2, then. Let's come back and see what this says to us. This just says, okay, I need to take a delta t forward here. And what I'll do is, here's my formula. This is exact, right? All I got to do is take my initial condition, Fourier transform it, multiply it by this factor. That gives me u hat, and I want u, which is just the inverse Fourier transform of it. So, yes, and that would be a delta t, exactly. Okay? So, what we're going to do here is calculate, let's call it the dispersion effect. And it's going to give us a solution u1, which is what we're going to do is we're going to take the FFT of this u naught, multiply it times I k squared delta t over 2, and then just inverse Fourier transform it. Cost me n log n to do this. Okay, so it's very, very fast. I'm not using an ODE solver, right? So when you first look at that equation, you think, oh, I'm stepping forward into the future. I've got a Fourier transform and everything. OD45 it forward into time. No, not in this case. I'm taking advantage of the fact that pretty much I know the exact solution. Okay? This highlights something more important that's there. Anytime you have information about your solutions and you're not making use of the fact of that you know something, you're being dumb. Okay? All right. You always take advantage. Every single time you can. Anything you know, you bring into the problem. If you know it, make use of it. Okay? Always, always, always. By the way, you don't have to make use of it. You can do this slow way that doesn't take advantage of anything. But this is what you really want to do when you program. Take advantage of things you know. I just took a delta t step forward, just using the dispersion. And now I want to take, instead of the dispersion, now I want to take the nonlinearity. So the nonlinearity has a formula there, and here it is. It just says if I want to go forward, if I have some initial condition to get delta t into the future, there's my formula. Now that becomes a delta t, and these u naughts are now u1. u1 is the initial condition for this. Okay? All right, so let's call this u2. u2 now is you just take this u1 and multiply it by exponent I u1 squared delta t. Okay? This is the exact solution to this thing. And I've taken advantage of that. 3. Step 4, I guess. Then you just say, all right, u naught is equal to u2.
Oh, in number 3, what's your...
Delta t over 2.
But that's the increment is delta t, right?
Mm-hmm.
And then number 3...
The increment is delta t again. Yeah, so...
But is t equal to 2 delta t, or is it equal to
No,
t at that point?
just delta t. I'm taking a delta t step forward. So it's kind of like you're saying, basically, I wanted to evolve the physics from 0 to delta t. Yeah. Mm-hmm. Mm-hmm. Yeah, that's right. That's right. Yeah. Oh, one parenthesis missing. So is everybody okay with that? There's your little algorithm. Boom, 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 boom. And oftentimes, if you can take advantage of that kind of structure, if you have your pieces of your dynamics that are sitting there in your PDE that it kind of be separated, and you know how to solve some of those pieces, this is awesome. A couple things that are nice about it. One, we talked about numerical stiffness, right? Here, totally just gets rid of numerical stiffness. Why? Because you've actually used exact solutions. Fantastic. It's great, right? So when you have things like that, in fact, when you think about what we talked about in terms of the integrating factor method with removing numerical stiffness, it's kind of something like this, but this is taking it one step further. And you're saying, just take steps independently. If delta t is small enough, you'll be in pretty good shape.